Welcome, everyone. We're very glad to have Ian Petrow here today to talk to us about relative trace formulas for GL2 and analytic number theory. Thank you, Ian.
Thank you very much for inviting me to speak here. So this talk will be something I've been advised that it should be a sort of maybe expository or sort of summer school style talk. So I don't know if I've actually achieved making it into that sort of style of talk, but hopefully it's something in that sort of direction. So I just want to start with sort of very basic things. We're just going to talk about modular forms at the very beginning of the talk. So there's sort of a well-known philosophy when you're studying modular forms that it's, if you want to study a single modular form or an L function in isolation, this is usually difficult, but modular forms arise naturally in families. And so we can use this to make some progress on kind of general difficult questions in the study of modular forms or L functions. So I'm just going to give the world's most basic example of how in practice we make use of families of modular forms. Probably the most basic example, if I just take F to be any holomorphic cusp form, say of weight K for the full modular group, it has a Fourier expansion of this sort. And let's just take the problem of how do we give sort of a non-trivial upper bound for these Fourier coefficients. So maybe the very first way I would say is the trivial, the 2 times trivial bound. Is just that we know that if the fact that F is cuspidal, well, that's equivalent to, if I take F and I multiply it by Y to the K over 2, where K is again the weight, this function is bounded on the upper half plane if and only if F is cuspidal. That's like an equivalent way of stating that F is cuspidal, and actually that generalizes to other congruent subgroups. And then from just computing the Fourier coefficient by an integral, you can quickly see that it has to be bounded by this. So this n to the k minus 1 over 2 is of course sort of that's sort of the truth, as we know from Deligne's solution of the Weil conjectures, that these Fourier coefficients are about this size, and that's sharp. Okay, so this double trivial bound is n to the 1/2 above the truth. But we can also use the family, and this is, I think, an idea going back to Steinberg, an old idea, to improve from this 1/2 to 1/4, and then maybe this is what is known as the first time trivial bound. The basic technique, the way typically in analytic number theory we use families of modular forms or L functions, is we pick one form that we're interested in, and we call it F naught, and I'm going to embed it in this space of modular forms of weight K, and maybe I'll think of it actually as a member of a basis for this space. So I'll write B, script B, for a basis for such a space of modular forms or cusp forms, in particular an orthonormal basis. And then we use the spectral completeness of this basis, and the way we get a hand on that is this formula called the Peterson Formula, which probably everybody in the room is already familiar with. So I've just written it here in detail. So here we get the product of 2 Fourier coefficients of F averaged over this basis times some normalizing factors is equal to the diagonal symbol that m is equal to n times the sum of Kloosterman sums. Okay, so here's the definition of the Kloosterman sum. And then it's useful to just think of these J Bessel functions in terms of a picture. So here I've just plotted the J1, J3, and J5, so you can take a look at it. And all that really matters for what follows is the behavior near 0 right here. And for those, we just have to know that J k minus 1 of x, well, actually, it's asymptotic to, so some constant x to the k minus 1. So you can see that for J1, 3, and 5 here. Okay, so then just from that simple bound, the fact that these Bessel functions are absolutely bounded and this simple bound near 1, we get this sort of bound for the Bessel function, which means that C is cutting off at a range of about square root of m times n. So if I just let m equal n now, I get an absolute value square here, and I can truncate the sum of Kloosterman sums at about size n, if m is equal to n. Okay, so now we need to use some real arithmetic input to go further than this. It doesn't take just families of modular forms. There's also some arithmetic input. Oh, I'm sorry, this absolute value bar was supposed to go outside the S here. But we use the Weil bound, which follows from Weil's solution of Riemann hypothesis for curves over finite fields, so just dimension 1. So that gives the optimal bound on these Kloosterman sums, and then you can do some basic analytic number theory to show that the right-hand side is going to be n plus a big O of the square root of n. And then there's another kind of crucial idea that gets used constantly in this sort of technique, which is the fact that these terms here are now all positive. So I can drop all but the term associated to f naught, the form I'm interested in, and I recover this this bound, which is, as you can see, is a little non-trivial, but the same sort of steps basically work if I do Moss forms instead of holomorphic forms. And then this became known as the trivial bound towards Riemannic, on top of which there have been many improvements by much more advanced techniques. So there's many other kind of more advanced applications of the Peterson formula along these sort of same sort of steps, using ideas like positivity and using this to capture the spectral completeness of a family. So you can study moments of L functions or zero density estimates or things like this. Okay. So the family, we talk a lot about families of automorphic forms in the subject, and there's no kind of rock hard definition of these that we can really count on. There's several sort of ad hoc definitions or working definitions, but at least the family that I'm talking about above, well, maybe I can expand the notation a little bit. Instead of just writing script B, I'll write B sub K and comma 1, 1. So in general, maybe I'll write script BIT to be the Moss forms with spectral parameter T, or IT you can say, and level Q and central character or Nabin type character chi. Okay, so often in this talk I'll write sort of things like union over the T in some range, because here it really, this BIT is almost always equal to 0, because there are, unless I have picked T very specially to be exactly a parameter corresponding to a Moss form. So that's a little, watch out for that. That's kind of like something I ought to explain. Okay, so here I've just written the classical Bergamon Kuznetsov formula now, which is the counterpart for Moss forms of the Peterson formula. Okay, so again, I have a product of two Fourier coefficients attached to Moss forms U. Okay, maybe here I should have, this maybe ought to have been IT and maybe like a union over all the T in R, okay? I don't think I'll use that convention later in the talk, but just in case, if I forget to write the subscript here, maybe I mean the union over all the possible spaces up and down the real line. Okay, well, on the real line and also including the possible non-tempered spectrum that's off the imaginary axis. But okay, that's not the point of this talk, so I won't dwell on that. Okay, so okay, but then you have this test function, which we're free to choose to kind of pick some range of spectral parameters. I've suppressed an Eisenstein series term, and you get something of the similar shape. You get the diagonal symbol that n is equal to n, and then this C of Q, so C of Q is Q times the product over the primes dividing Q of 1 plus 1 over P. And that just represents the dimension of the space of forms of level Q. And so this piece is related to the Plancherel measure on the real line. And so that kind of captures the mass in this test function H. Okay. And then again, we have a sum of Kloosterman sums. And if I'm doing this really for a general central character, there's a factor of chi bar inside the Kloosterman sum here. And then this is a general test function, which sometimes I'll write this later in the talk. I'll write this just as H infinity of 4 pi square root mn over C. Okay, so the Kuznetsov formula has many more applications actually than the classical Peterson formula. You can study eigenvalue statistics of Moss forms or large sieve inequalities. And one of the main important features of this is these integral transforms that show up on the right-hand side of the formula can actually be inverted. So we can study sums of Kloosterman sums in terms of sums of Fourier coefficients of Moss forms. So there's many applications of this way to kind of this spectral interpretation of sums of Kloosterman sums. But again, that's a subject of a different talk, so I'll kind of leave that aside. So something that I've worked on in particular is subconvexity and the applications to subconvexity. So maybe I'll kind of focus on the applications of this Kuznetsov formula to subconvexity. So here's an example application. So it's a very old one. This kind of goes, but this goes back to 2002. So Duke, Friedlander, and Ivanich studied an amplified fourth moment of L functions over this family. So U is a Moss form of level Q and central character chi. And they were able to prove the first subconvexity result for all F on GL2 over the rationals. So this holds for F of level Q and any central character, and you save a small amount over the convexity bound. So it's what I would really like to do is write down what this amplified fourth moment is to say how they prove this, but I don't really kind of like want to take so much space on the slide. I'll just give kind of a more advanced and more recent version of the same idea of studying a moment of L functions to derive a subconvexity result. So there's been kind of several papers in the last few years, in the last like maybe 2 years by Carell and Young and Blomer and Kahn, and then most recently and with the best exponent, Blomer, Humphreys, Kahn, and Milanovic. So they were able to study moments of L functions. And so let's just take trivial central character in this case, and level Q. And then if we look at the L functions attached to these Moss forms with maybe spectral parameters going up to some bounded height, so less than 1 is maybe less than or equal to 100 or so. Then we can go all the way up and take the fifth power of this now and show that this is bounded by Q to the 1 plus theta over 3 plus epsilon. So this theta is the best bound towards the Ramanujan conjecture for Moss forms. Okay, so I guess Carell and Young did holomorphic forms and got this without the divided by 3 here, and Blomer and Kahn did Moss forms, and those two papers appeared, I think, within a day of each other on Archive. And then this most recent paper got theta over 3 instead of theta. At least if I assume the Ramanujan conjecture, these are all Lindelof on average, or equivalently, if I ignore this factor here, these are all Lindelof on average upper bounds. And we also know from work of Waltzberger, let's work on my handwriting, that these central values are always positive in this case. So this is really using very strongly that I have trivial central character here. And so we can do the same sort of positivity argument that I showed in the simple example on slide 2, to drop all but one of the terms here and then take 1/5 powers of both sides. And this leads to the best currently known subconvexity exponent in level aspect. For GL2 over Q with trivial central character. So the exponent would be 1/5 if I assume Ramanujan conjecture, and if not, it's a little bit above that. Okay, so I want to kind of, my goal here is to just show you a much more advanced application of this idea of embedding in a family and then using positivity to get somewhere. So the kind of crucial thing here is always playing the size of the family, which shows up on this side in terms of the estimate, off the average conductor of these L functions. So in this particular family here, the size of this family is about Q to the 1 plus epsilon. Okay, and then also the average conductors here are also size Q. So it's often helpful to have the finite or otherwise said non-Archimedean examples and also Archimedean examples, and kind of make sure you understand the analogies between these two sides. So let's just mention what the Archimedean analog of this might be. So similarly, if I take Moss forms of first for SL2Z with trivial central character, and I take the spectral parameters in a large window, say from T to 2T. So here, all of the conductors, the analytic conductors of all the forms in this family here are all about size T, capital T squared. And also the number of forms appearing here under Weil's law is also about T squared. So in this sense, you have the size of the family is about equal to the size of the conductor. So these are both T squared and these are both Q. Okay, so in the Archimedean example, there's an obvious way to shrink the family. So instead of taking a big window of size T from T to 2T, capital T to capital 2T, let's take a small window, say roughly T to T plus T to the epsilon for any small epsilon. So it turns out that rather than studying like a large moment, like the 5th moment or the 6th moment for these Moss form L functions in a large window, from the point of view of analytic number theory, it's much more effective to study a very short window in a smaller moment. So this was done a long time ago by Ivich. He studied the 3rd moment in this small family and got, again, a Lindelof on average upper bound for this moment of L functions. So the situation here with regards to the size of the family of the conductor is much more favorable. So the size of the family now is about T to the 1 plus epsilon when I'm in this very small window, and all the conductors remain size T squared. So this actually leads to a Weil strength bound, so that the barrier moment here would be the 2nd moment, and Ivich could go a whole power above the barrier moment and actually prove that the Weil bound in the spectral aspect, in the eigenvalue aspect for these L functions. So he did this rather explicitly using a Morohashi formula. So I don't want to kind of give a talk about that. That's the subject of a different talk. but I'll just mention it. So he used very explicitly like the Motohashi formula from Motohashi's book, which has like 7 different terms, and he calculated all of them and got this estimate. So coming back to the level aspect, actually, so if Q is prime, then I don't think there's sort of any obvious thin subfamily of this family of forms of level Q and say trivial central character. Again, Q prime here. On the other hand, so Connery and Ivanich, so what they observed that if I take chi to be the quadratic character, and let's just maybe stick to prime powers for right now. So chi is just the Legendre symbol mod p. Then if I take the forms of level Q, so here this includes both. So I'm still thinking about Q prime in this line right here. So this includes both forms of level 1 considered as old forms inside forms of level Q, and also primitive forms of level Q. And if I twist them by the quadratic character, these are all, so the size of this family, I kind of take a smaller family and then twist them all up to a higher level. So the size of this family is just the size of this piece, and that's about Q to the 1 plus epsilon. But now all the forms here, these twisted forms, are all conductor Q. So at least if I'm dealing with conductor Q squared, where again, Q is a prime in this example, I've got sort of a situation like this where I've got a thin family with large conductors. So using this, they were able to prove a cubic moment estimate. So again, I sum over kind of a similar family here. And the key point here, any finite number would do for this 5, but this Q to the 1 plus, oh, sorry, here I've made a mistake. This should just be epsilon, not 1 plus epsilon. So it's nice when if you have the pen going at the same time that you're giving the talk and you find an error, you can just kind of scribble it out. So anyway, so here this is again, this is like a Lindelof on average upper bound in Q aspect, and it's anything polynomial in T aspect, and that we don't care so much about anymore. So maybe just like an interesting remark also that Ivich versus Connery-Ivanich. So this work of Connery-Ivanich actually came out before Ivich, and Ivich has some remark in his paper saying like, oh, there's also this work of Connery-Ivanich, which is similar but in Q aspect, but the technique is completely different because they don't use a Motohashi formula at all in Connery-Ivanich's work. So I think that's turned out to be, in hindsight, for many years later, there very much is a Motohashi. That's not really correct. This work of Connery-Ivanich is very much based on a Motohashi formula, which is driving this and making this cubic moment possible, which otherwise this would be way beyond what we would expect to be attackable with kind of current techniques. So again, I'm still dealing with like ancient history here, but this led to Weil strength subconvexity bounds for these Moss forms twisted by the quadratic character, and also Dirichlet L functions of quadratic characters. This is still kind of a very constrained case. This doesn't come close to covering all the possible automorphic forms of conductor Q squared. This is just one very particular cases. But the kind of what's holding us back from generalizing this result is finding the right families of automorphic forms. So to kind of really describe what's going on here, I need to kind of introduce some representation theory, but I'm kind of try to explain it in a way that, okay, if you already know this story, you're going to be bored for the next few slides. But if you don't, maybe this is kind of a quick and dirty introduction, and it may encourage you to learn some more about this. The point so I'll give you the point away now before kind of going through the next few slides. So the punchline is if Q is not prime, but is anything higher than a prime, then we actually can find thin subfamilies of the trivial central character forms of level Q. So Q is no longer prime, Q is now anything. In fact, this is going to be useful when Q is not a prime. If you don't know what this is, all you need to know is that if I have a cuspidal new form F, I can turn this into a function on GL2. And then by taking some translates, I can build up a representation out of this function. So a big infinite dimensional space just by translating that vector around. And this is going to be a representation now of GL2 of the Adele ring. So, okay, hopefully you've at least seen that in passing someplace. So for every F, I'll write its associated automorphic representation by pi F. And unlike the classical modular forms, the main advantage of going to the representations is that you can't just take like a function on the upper half plane and factor it over places and use multiplicativity. But if we have this representation, it really does factor over all the places, all the primes, and also a component at infinity of the rational numbers. Okay, so it's I can write it as a restricted tensor product of representations at every prime. All that's important is that given an F, I can construct its representation, and then I can talk about its representation at P. Okay, so each of these pi P's turns out to be an irreducible unitary infinite dimensional representation of GL2 QP. And the nice thing is now we can bring in some input from representation theory. So there's a classification of these things. They either come in one of three flavors. They're either principal series, special representations, or supercuspidal representations. So I have to describe kind of a parameterization of these things. So here I'm going to for this slide, Q is now going to be an odd prime power. And I'm also going to restrict to the trivial central character representations, which cuts down the set of representations by quite a lot. But just for simplicity, I'm going to do that. And I'm also going to ignore any representations which would arise from failure of the Ramanujan conjecture for Hecke eigenvalues. So these are just going to be the tempered representations. So you might just think we're kind of throwing away things that shouldn't exist if we believe Ramanujan conjecture to be true. So these principal series representations are actually parameterized by a number S, which I'll take to be imaginary, and it lives on this circle. And also chi, a primitive Dirichlet character mod Q. So there's an isomorphism. So this is some representation. I won't tell you how it's constructed, but it's some representation of this group. And if this number S, if I take chi and I take its complex conjugate and replace S by minus S, I get the same representation. And otherwise, these are distinct. Again, with this trivial central character assumption, okay, there's not very many special representations. There's only 4 of them total. There's something special called the Steinberg representation, and you just get 4 twists of it. So there's some representation ST, which I won't tell you what it is. But then there's only 4 of them, so you just get Steinberg, and then Steinberg twisted by each of these 4 things. So the point here of this pi I over log p is that's exactly halfway around this circle here. So the point is that this is order 2. If I square that, then I get trivial back. And then this is going to be the Legendre symbol. Okay, and then I won't even tell you anything about supercuspidal representations right now. So what I want to explain is that in Conry and Ivanyich's situations, remember they were taking this space, maybe this basis of forms of, I'll say level P, and trivial central character. So if I look at the associated, so if I take an F in here and I look at the associated representation pi F and I look at its P component, this P component is one of these three things. It's either this Steinberg twisted by the Legendre symbol, or it's Steinberg twisted by this other quadratic character, or it's on one of these circles worth of principal series representations. So this is all, okay, I left a blank slide here because I just thought it would be useful just to draw a picture. I don't know about you, but I remember everything better if I just have a picture. So here's conductors. So here's conductor 1 and conductor P and conductor P squared and P cubed and P to the fourth. The useful thing about this classification is you can read off the conductors from this classification of the P representations. So again, I'll emphasize that I'm doing just the tempered part here. So I'm ignoring any possible failures of Ramanujan that could happen just to make the picture a little bit simpler. So in level 1, there's just a single circle worth of these representations. So every point on this circle corresponds to a representation. And these are these representations alpha S, where S runs through this, is a pure imaginary number that goes from 0 to 2 pi I over log P. Okay. And then where I am on this circle, oops, what have I done? Somehow I went to the next slide. Where you are in the circle, why does it make me do that? Where you are in the circle corresponds exactly to your Satake parameter at P if I'm in this unramified situation of conductor 1. And then in level P, there's just 2 representations. And these are this thing called the Steinberg representation. And then there's Steinberg twisted by sort of halfway around the circle. And then in P squared, you have, this is going to just be the quadratic twist of this lower circle. So it's alpha S and this Legendre symbol. Okay, and then you have the quadratic twists of these 2 lower guys. So I'll say this twisted by Legendre symbol, and this is this twisted by Legendre symbol and this other quadratic twist. But then there's a bunch of other circles which correspond to other characters mod P squared. So this is alpha S chi, where the conductor of chi is equal to P, but all the representations here are conductor P squared. And then for these principal series, there's nothing of conductor P cubed, and then there's a whole lot of circles, each corresponding to chi of conductor of chi equals to P squared, and all of these are going to be conductor P to the fourth. Okay, and then there's also some things called supercuspidal representations. And they don't occur until I get to level P squared, but then they occur in every level. Okay, so that's it. That's all of the representations. So just to sort of say that again in words, each of these 3 things, which are the things that Connery and Ivanich are twisting up to level P squared, have conductor P cubed. So I'll say, so Connery and Ivanich take this piece and these 2 pieces, and then by taking quadratic twists, this one goes up here, this one goes here, and this one goes here. So the family, if I just look at a single prime, the family that Connery and Ivanich are studying is the union of this one and these 2 representations here. And they're all of conductor P squared. Okay, but that's not all that's in this picture. So there's also P minus 3 over 2 other circles of principal series representations of conductor P squared. So that's for all these other chi's, which are not equal to the Legendre symbol. And there's this one isomorphism between them. So those correspond to all these other circles out here. So that's like p minus 1, and then I subtract the trivial representation and the quadratic character to get down to p minus 3, and then it's divided by 2 for these isomorphisms. And similarly, if I go up to the p to the 4th representations, there's this many circles worth of representations of the conductor p to the 4th. And they're parameterized by the primitive characters mod p squared, and then etc. Okay, so if I take, so this was all locally at a single prime, so q is a prime power. Then if I take a form of, so this star here means a new form now. So if I take something of conductor q and character chi squared, then the crucial fact here is if I take f and I twist it up by chi bar, the local component of this thing is going to be exactly hit the representation that's that circle. So if I take an f, which is conductor q and central character chi squared, and now I twist like this, then okay, so this chi bar transforms the central character by chi bar squared, so I get back to this having trivial central character, and that just corresponds to the circle that matches chi. So actually, by taking these sorts of families, I take this family and I twist it all by chi bar, that hit that each one of those families, if I, for each choice of chi bar, picks out a single circle's worth of principal series representations. And so I actually have a family that I can pick out with the Kuznetsov formula that individually picks out one of these pieces at a time. And so that's how we get a thin family at P in level aspect. Okay, so, and the point is that the fact that these come from taking kind of one of these standard families and twisting by a character is that I can use the Kuznetsov formula to capture the family having this specified local component at P. And those are going to be my thin families. So I can think about this two ways. I can say either I take the pi, which have this particular circle's worth of principal series representations at P, and I can, that's the same thing as just taking the representations associated to pi in this space of forms that I understand well, and then I have a Kuznetsov formula for and twisting them by chi bar. And again, we get this nice thin family situation where the size of the family is q to the 1 plus epsilon, but they have large conductors. Using these families, we were able to prove the Weil bounds for all of these forms occurring in these families, and then also in particular L 1/2 chi for chi any Dirichlet character of any modulus. So this is kind of already a few years ago, and so this was joint work with myself and Matt Young. Okay, so there's one obvious other part of this picture that's sort of missing so far. So Conry and Ivanic did kind of, or not those, just the families corresponding to these, and we were able to do cubic moments over family corresponding to a single circle here. But there's also all of these isolated supercuspidal representations on this side of the picture. The obvious next thing to do would be to try to do supercuspidals. But in this case, there's no kind of classical Kuznetsov formula that suffices to pick out one of these supercuspidal representations. So this is definitely something that is still open, but it's something that kind of is current work in progress with Yuki Hugh and Matt Young. So I don't have anything to report on that, so that I will not say another word about that, but it's sort of future work. Okay, so let me come back to this Kuznetsov formula, because that's kind of what this, I'm trying to center this talk around is Fourier trace formulas in general. So probably the most direct proof of this Kuznetsov formula goes by certain automorphic forms called Poincare series. So you can find the proof along That's probably the most direct proof, but maybe it takes a little bit more cleverness. So I don't want to talk about that, and I want to talk about a different sort of proof of this Kuznetsov formula that maybe generalizes in different ways. So I'm going to sort of talk about a kind of classical version of this, and then I'm going to talk about an adelic version of this. And so maybe I'll go quickly through this version, but hopefully this kind of primes the pump a little bit. So if I take f, any smooth compactly supported function now on SL2R, and I want to assume that it's invariant on the left and the right by SO2 as a subgroup of SL2R. So just the matrices, cosine, sine, minus sine. Oops. Okay, I want my dark blue back. Then I can write down a kernel function by averaging. So I take this f and I'm going to sum it over all the SL2Z matrices, and I'm going to translate on the left and translate on the right by elements of SL2R, and this gives me a kernel function. Okay, and so remember, f is I've chosen to be compactly supported, so there's kind of no convergence problems here at all. I can write down this sum. And then I can get sort of what's called a pre-chase formula out of this kernel function by doing a spectral expansion. Okay, so I'm going to have that this kernel function is equal to a term from the cuspidal spectrum, from the continuous spectrum, and also a residual spectrum. So because this is just a talk, I'm going to sort of completely ignore these two terms and just say what this cuspidal term is. This is just going to be a sum over some orthonormal basis for level 1 trivial central character MOS forms with any spectral parameter. And so I get C bar of Y, and then also C of X acted on by a certain operator. So this operator is a right translation operator, so it's defined by this integral. So because F is by SO2 invariant and is compactly supported, this so it's built out of the right regular representation. So you get sort of right translation by Y here, but it's like a projection operator. It operates on a finite dimensional space, so it's much easier to understand than the full right translation operator itself. Okay, so once you have this pre-chase formula, which maybe you're familiar with this sort of thing if you've read papers on supernorm problem, but you can also take this pre-trace formula and integrate it along unipotent orbits. So here, this N, I should have written what this is, but this is the subgroup of matrices that are like 1x01. And so here's an additive character, and then we integrate this kernel function against this additive character, and then, okay, so there's one supplementary integral here, but let's not dwell on that. So if you take this integral and you compute it 2 different ways, one by replacing this k by this spectral expansion, well, we should choose the C to be eigenvectors of this operator. Okay, so it turns out what this will do if I choose these to be eigenvectors is that the eigenvalue for this vector is just going to be h of t, where this t phi is the spectral parameter associated to the phi, and h is what's called the Selberg transform of f. And these h of t's there's a family of these that are the usual ones that you're used to from the usual behavior of the Kuznetsov formula. And then to evaluate the geometric side, that is using this form of the kernel, we just use the Bruhat decomposition in this kind of explicit form. And then you can already see the Kuznetsov formula coming out. So these terms will lead to your diagonal contribution. Here I'm going to have my sum over C, and here you can see how this will lead you to Kloosterman sums. Okay, and then we end up recovering sums of Kloosterman sums. Okay, so to really explain what kind of the next steps are, I have to present this in an adelic manner. So more generally, what we're going to do is we're going to, instead of looking at functions f that were on SL2R, we're going to look at functions f that are on now GL2 of the adels, and that are going to transform under the center. So this thing here is the center, so it's diagonal matrices like this, such that Z is in the adels of Q. And here, this is a Hecke character over Q, but you can just think of omega as a primitive Dirichlet character. And so I'm only going to look at test functions on GL2 of the adels that factor over places. So it's going to have some function f infinity on GL2 of R, maybe the positive determinant matrices in GL2R, and then also a bunch of other functions on FP, one for each P. So I have to kind of, in the same way as before, I chose this function to be compactly supported, and smooth. So here I'm going to make some sort of similar assumptions. So I'm going to assume that these functions on the finite P's are going to be locally constant and compactly supported mod center, and I'm also going to assume that they're normal. So here, so f star of G is by definition f G inverse complex conjugate, and then f convolve H of X is just going to be equal to this integral. So it's going to be f of Y H of X Y inverse dy. Okay, so the point of this is it's going to apply this operator is normal, so I can diagonalize it. Okay, so I'm also going to assume that for almost all P, this FP is basically just the indicator function of GL2 ZP. That's the maximal compact in GL2 QP. And if there's a central character, well, it's going to transform by the central character. But basically, you should think of this as the indicator function of GL2 ZP. And so maybe I'll call such prime the almost all P. These will be unramified. So I still have many slides to go and only 12 minutes. So I should maybe kind of speed up. Okay, so just like before, I have this adelic pre-trace formula now, which is now holds for X and Y in 2 copies of GL2 over the adels. And again, I'm going to completely ignore what these 2 terms are. There's something similar. But I have similarly a geometric kernel and a cuspidal part. And I'm going to take this B naught is now going to be an orthonormal basis of cusp forms consisting of eigenvectors for this operator. And so, and also those will just be those forms that have an SO2 cross K fixed vector, where this K, what is that? That's so these hypotheses here, so it's kind of just an easy exercise to show that such an F P is by K invariant for K a compact, K a compact open subgroup in here. So, so this K is maybe the product over all the places of those compact open subgroups that we get out of, that are produced by the test function F. So again, instead of integrating on a literal circle, I integrate on this adelic, 2 adelic circles. And then I get a more general Fourier trace formula out of this, which I'm not going to write down completely. But I'll just mention that this right regular representation with the test function F on one of these vectors that I've assumed to be an eigenvector. So the infinity component is going to give me exactly the same test function, just the way the kind of classical version did. And then I'm also going to have a different eigenvalue that corresponds to the behavior at all the finitely many primes. So the cuspidal piece of this adelic formula is going to come out like this. I have two Fourier coefficients, which you can define just like in the classical way. This piece looks exactly like the classical Kuznetsov formula. And then I'm going to have these eigenvalues of this operator, which give me some extra flexibility now. At the same time, the geometric side of this kind of like, of this Fourier trace formula has this sort of generalized Kloosterman sum at P. So it equals this double p-adic integral. Oh, I should mention for all this, so I'm following here work of Knightley and Lee for this presentation. Okay, so you have, this is what the kind of generalized Kloosterman sum at P is, and this level of generality where I have not really, I've only made sort of mild hypotheses on the test function at each place P. So if P is one of these unramified primes for F, where I've assumed I just have the maximal compact, then this KP is actually, is literally just this classical Kloosterman sum with a little bit of translation. So here I've written mu as the part at P and the part away from P. And so I get, so there's always sort of this translation that this mu kind of looks like 1 over c squared in the classical situation. And so I really get just literally these old-fashioned Kloosterman sums as long as I'm at unramified primes. And say if there were no ramified primes for F, then I could just use the twisted multiplicativity and multiply these back together to get an actual Kloosterman sum with, not just with a prime power here in the modulus. So the goal would be, if I have this for the cuspidal piece, is to pick these, pick F cleverly so that these eigenvalues here are going to vanish for many, many of the forms phi in this basis. And so I want to kind of choose the F to capture a family of automorphic forms that I'm interested in. So I just want to, the goal is going to be to choose F so that this operator acting on phi is just 0 as long as if phi is outside this family, or maybe sort of a spectral closure of that family. So just as an example, if I take this sort of F, and I just assume it's ramified at a single prime, which I'll call P, and I take the indicator function of this K1 Pn subgroup, this is just going to return the classical Kloosterman, the classical Kuznetsov formula. So here, these are all going to vanish unless the conductor of my representation divides P to the n. If I plug P to the n here. Okay, and in that case, I get, again, this Kloosterman sum, but then the fact that I have this Kloosterman sum is vanishing in a much wider range of mu's gives me the condition that C is equivalent to 0 mod P to the n in the classical Kloosterman. The classical Kuznetsov formula. Okay, but the advantage now, after we've sort of like redone this adelically, is that now I can put in supercuspidal. I can build up some of these supercuspidal representations and have sort of generalized Kuznetsov formulas for supercuspidal representations at P. So let me explain what I mean by that. So let me fix pi 0 is going to be a specified supercuspidal representation of GL2 QP. I'm always just interested in trivial central character. And so if I choose my test function to be the standard test function at all the unramified places, and at P, I'm going to choose it to be this matrix coefficient. So it's the diagonal matrix coefficient with respect to the new vector. So I think, as is well known, this is going to always give you 0, except if phi is a vector in a global representation that has exactly this specified supercuspidal as its P component. And even nicer than that, it's actually going to annihilate all the vectors in this representation except those that are proportional to the new vector, if I use the new form to construct the matrix coefficient. So this operator, R f, if I choose f as up here, is going to pick out exactly this sort of spectrally completed family. So it's going to be all the forms f of the same conductor as pi naught, which is my specified supercuspidal, and such that if I build the representation out of pi and look at its p component, that's isomorphic to my specified supercuspidal. So these are sort of specified supercuspidal families. So an issue with this of just working out what, evaluating these p-adic integrals is that these generalized Kloosterman sums for this choice of test function kind of become a complicated mess. And particularly they're given by a double sum instead of like a single sum like we would get with a classical Kloosterman sum. At least you can say, you can kind of still analyze where they vanish. So they're still 0 unless these m and n are away from this parameter mu. So remember, you should think of this mu as being like 1 over c squared if c is the usual modulus of Kloosterman sum in the classical situation. So we can at least understand the support of these Kloosterman sums. Oops, I didn't want to do that. So I should mention there's perhaps also a better way to do this than just picking a single matrix coefficient as my test function in this general Fourier trace formula. Yuke last year used minimal vector theory, which has been spread across a few papers due to Hugh, Nelson, and Saha, sometimes together and sometimes in separate papers. And so UK should give this talk, if I was going to expand kind of this slide into a whole talk, UK would have to give that talk, so I'll suppress most of the details. But using this minimal vector theory, you can give a simpler formula for the Kloosterman sum that corresponds by choosing F not to just be one matrix, but to be some linear combination of matrix coefficients. There's a cost to this, is that the spectral side gets expanded a bit. So if my specified supercuspidal has odd conductor exponent, then I only expand the spectral side by like O of 1, but if I have even conductor exponent, you're expanding by like an O of P. So it gets kind of worse. But at least it's nice to be able to write down explicitly what that Kloosterman sum, that generalized Kloosterman sum corresponding to the supercuspidal family is. So I have to define some things. So if you look at this formula, maybe it's best to read this slide bottom to top. So you can compute, or UK computes that this is what the formula is. So first of all, so EL, okay, so the first thing you need to know is that you can construct supercuspidal representations by compact induction theory. And so given a pair where L over QP is a quadratic extension of QP and theta is a character of L cross, you can construct a supercuspidal representation of GL2 QP out of that. And this ensures trivial central character. So here I have sort of using a Postnikov formula for OL. Here pi is a uniformizer for OL. You can convert multiplicative characters to additive characters if I'm 1 plus a uniformizer. And this L theta is the constant that corresponds to theta. And if I make out of that this number L, okay, so maybe this is bad notation actually. This L is not equal to this L. This L is just is a number, or not a number, but it's elements of this, translated by a prime, which should maybe, yeah, no, okay, that's the prime in the base field. And this I naught is a typo for this quantity, so it's the conductor. Okay, so this actually is now conductor exponent. I should be more clear about that too. And this is the ramification index of L over Q, P. So these, again, I can understand what their support is. They vanish unless K is sufficiently large. And then if K is sufficiently large, you get this sort of formula where this L is this L. Okay, so that's kind of nice to see. And in just sort of the last 2 minutes, I want to kind of justify me having talked about this Fourier trace formula in this greater level of generality of picking an arbitrary test function an arbitrary adelic test function. So in general, if I have some family of GL2 forms, often we take sort of a spectrally complete family that's a little larger. So maybe if I think of F as like the level, the conductor Q forms, I would take all the level Q forms as being sort of a spectrally complete family, which is not too much larger than the family I'm interested in, but is sort of spectrally complete. Or I might think of this also as like in T aspect in Archimedean, at the Archimedean place. If I want my spectral parameters to lie in some interval, well, I'm going to take a test function and spread them out over the whole line, but with a test function. And so that's kind of like how we'll think of this spectrally complete family. Okay, so to get sort of the applications that I'm leading up to here, you need this sort of better kind of schematic trace formula. So here, these are Hecke eigenvalues and not Fourier coefficients, and these are some weights. And here I get CF, which are some set of moduli, which I can't specify without specifying the test function. And this not too much larger condition here just means that this sum over the completed family with respect to these weights is bounded in terms of the size of the family. So these are sort of hypotheses that come up in many situations. We have to define sort of a modulus parameter. So I'll define Q now to be the maximal integer which divides all of the C in the set of moduli. So as I alluded to, there's a general issue here, which is that Fourier coefficients are not in general equal to Hecke eigenvalues, except if I'm dealing with new forms. So we always have to deal with this problem, and I'm just going to make a hypothesis out of it. So in the classical situation, you can try to choose an orthonormal basis for the eigenspaces, which are of larger dimension in general. And there's been a lot of work by many people over many years about clever ways to choose these bases. We luck out in the supercuspal situation if I choose a matrix coefficient, because actually these matrix coefficients as test functions, the R of F is now going to annihilate everything except on the line of the new form. So you kind of get Fourier coefficients equal to Hecke eigenvalues very slickly if you're using these matrix coefficients. Or if you're using these minimal vectors, the same thing happens there. So I'm going to make a couple hypotheses. So first, this one is just the family that this operator annihilates everything except for the forms in my completed family. And then this second hypothesis is just sort of writing down formally the fact that I need some device to go between Fourier coefficients and Hecke eigenvalues. So here, this is going to be an orthonormal basis of eigenvectors for this representation on this finite dimensional space. And then if these eigenvalues times these Fourier coefficients, if I can build up some weights such that that's these weights times the Hecke eigenvalues, then I'm going to directly get a formula like this with those weights and Hecke eigenvalues. Okay. So there's a couple more hypotheses, which I'll try to go through very quickly because I'm already over time. So this one is something technical, which I will kind of leave out for now. But the main two interesting things here, so if you just need two things to get the theorem I'm leading up to, which is going to be a general large sieve inequality for all of these sorts of families. So the first is modulus versus the size of the family. So remember, Q was the number which divided all of the moduli that show up in this generalized Kuznetsov formula. And I have to have that there's this kind of lower bound of that modulus in terms of the size of the family that I'm interested in. So this can be, as long as that modulus is bigger than the size of the family or just less than it by about a q to the epsilon, it's okay. And the second thing is that we don't actually need nice bounds on these generalized Kloosterman sums themselves, but we need nice bounds on their Fourier-Mellin transforms instead. So if I just kind of write down the Fourier-Mellin transform of these generalized Kloosterman sums in this classical sort of way, what we need is a kind of, they need to be sort of almost bounded for each C. So I have this sort of L infinity estimate for all of these Fourier transforms of these Kloosterman sums. So given these two things, we get this theorem. So if F is a family satisfying kind of the hypotheses above, which can be picked out by specifying an adelic F in this adelic pretrace formula, then for all sequences, we get a sharp large sieve inequality. So this is the kind of up to this epsilon is the best large sieve inequality you can hope for one of these families. So you might say, okay, this is great, but this is sort of contrived. Like, how could you possibly come up with examples that fit all of these hypotheses that you've packed in here? So, okay, so there's several examples. So there's kind of the classical example. And then I talked kind of already a lot about these principal series and supercuspidal families. So we could check that all of these satisfy the hypotheses that I mentioned. It's interesting to note that the generalized Kloosterman sum for one of these using a matrix coefficient to pick out that supercuspidal representation is like pretty complicated if you write down the Kloosterman sum, but it has a really simple Mellin transform. So there's a bunch of kind of simpler factors that I've suppressed, but it actually kind of just looks like this this Gauss sum on the quadratic extension of QP. Instead of just like a Q Gauss sum, it's like a L Gauss sum for that quadratic extension. You can do intermediate things. And lastly, I'll just mention that there's a nice sort of non-example. So I think Matt has talked a lot about this paper of Ivanich and Lee, which looks at basically like you take forms of level Q with any central character, not just specifying a particular central character. And this actually fails to have there's the naive expectation of this sort of sharp large sieve inequality is actually false for that family. And so I should mention that this family fails these hypotheses. And which does it fail? It fails the modulus first size hypothesis, but satisfies all the other hypotheses. So that's why this family fails to have this sharp large sieve inequality. So I'm sorry I went over, but now I'm done. And thanks for letting me get to my last slide.